Hi, welcome to what is hopefully gonna be a short video just explaining what differential mode and common mode signals are and why do we actually care about them. So I'd like to begin this discussion with an example of differential mode signal. So as you can see here, I have a microphone, and this microphone uses what it's called an XLR connector, which looks like this. Hopefully you can see it. And I have an XLR cable here, and if you take a look at it, it has three connectors. I've just taken the body of the connector off, and if you take a look at it, hopefully the camera will focus on this. You can see that there are three wires in it: a red wire, a white wire, and what seems like just bare copper wire. So this XLR connector carries what is a typical differential mode signal. And by differential mode, we mean that the signal consists of what we call a hot and a cold signal. And this third connector is actually a shield that goes along the entire length of this mic cable. So let's go ahead and take a look what a differential mode signal looks like on paper. Let's start off from basics here. Why do we need differential signaling? The word differential suggests that there is something to do with a difference going on, right? So let's just consider the most basic case of a signal traveling from one point, so the signal source, to the receiver. So if I draw this real quick, let's consider that we have a signal source over here, goes to ground, and I use a cable to connect this signal source through long distance to my receiver over here. Could be an amplifier, could be whatever, right? And crucially, this amplifier is also supplied by ground. So this is all well and good, right? But what if, right now, what if this ground and this ground are different? So our premise of circuit analysis until this point in time has been grounded, well, no pun intended, in the fact that the grounds everywhere are at the same potential, right? So if we just go ahead and label these few nodes real quick, node 1, 2, 3, 4, the signal voltage is going to be the voltage at node 1 minus the voltage at node 2. And the voltage seen by the amplifier is going to be the voltage at node 3 minus the voltage at node 4, right? So, thus far, our assumption has been voltage at node 4 equals to the voltage at node 2. Therefore, these two are the same. Let's just take simultaneous equations between this and this. We are going to arrive at the voltage at the source is equal to the voltage at the amplifier. Well, this whole thing breaks if this assumption is violated. And I'm going to tell you right now that this assumption is actually not true in the real world. Why? So an example of when this would become a problem is when this signal source bit of the circuit is really far away from this, the receiver end. And there are lots of cases where this might be. Take, for example, a long telephone cable. Telephones are actually differential signals just because of this reason. Is that this ground, the ground of your phone, well, in your house, is almost certainly not the same as the ground of the receiver or, well, whatever central processing the telephone relies on. And at a very simple level, this difference arises because recall Kirchhoff's current law. Whatever current flows out of this signal source has to go all the way through this cable into the amp, back through ground, and return. Current cannot flow if there is no loop. So think about this node and this node. How are these two nodes connected? such that this current can flow. Well, there has to be a wire here somehow, right? There has to be some sort of wire here connecting these two nodes. And this wire is not perfect. So there is some sort of resistance or impedance for that matter that is in series with this wire, right? When this occurs, as soon as there's a current, Ohm's law tells us that, assuming that the current flows this way, this point has to be at a higher potential than this point. So now, this node is higher in voltage than this node. So this assumption is wrong, right? So the voltage seen by the amplifier is no longer equal to the voltage generated by our signal source. So, well, when is this going to be a big problem? This is going to be a big problem if we have some sort of, let's say, electromagnetic interference. So there's like cosmic rays or whatever that, let's just say, induces a changing magnetic field, for example, within this area. So the wire goes here, comes back. As soon as there is any sort of electromagnetic energy that is interacting with this loop, what do you get? You get a loop that has some sort of magnetic field going into it. You're going to get an EMF, right? This EMF is going to be distributed across this entire thing. And crucially, it's going to flow through this ground node. This ground connection, right? So there is going to be a current that flows through this ground connection just by courtesy of whatever cosmic rays or like, antenna transmitters or your phone or whatever that is just close by. Changing magnetic fields induces a voltage across this ground node. And this voltage is essentially going to be noise because it's not coming from this. It's external. So how do we solve this? So the way we mitigate this issue is we introduce differential signaling. So now we have this signal source over here. I introduce a third conductor. So just now we had signal and ground. Now we have two signals and ground. So I'm just going to name this node the hot node and this node the cold node, right? So similarly, over here, we have the cold node of the receiver and the hot node of the receiver. Now, whatever voltage difference that manifests itself across the ground at this location and the ground of the receiver doesn't matter, because what this amp cares about is essentially V at the hot minus V at the cold. This thing is going to equal to the voltage of the signal source regardless of whatever the ground potentials at this end and this end are. Because if you take a look at this expression over here, there is absolutely no dependence on ground, right? So effectively, we have eliminated the whole noise problem that is caused by electromagnetic interference just because we have switched from, a conventional way of transmitting a signal across a long cable into a differential scheme. Well, then you might ask, what happens if there is a changing magnetic field here, right? In between the hot and cold conductors. Well, in a real world scenario, these hot and cold conductors are constructed of what is called twisted pairs. So inside the wire, this hot wire goes like this, and the cold wire goes like this. So they're twisted together in such a way that the area between them, so the separation between these two conductors, is very, very small. And if you recall, we have phi equals to BAN, right? So if the area is very small, almost zero, phi is essentially going to go to zero. And we're not going to get that much of an EMF that is formed between the hot and the cold side, so that will affect the voltage of the signal seen by the amplifier, that is going to manifest as noise. So inside the microphone is this. There is a coil that has a ferrite or whatever magnetic material goes through its core, and when sound waves come in, it vibrates, and therefore a voltage is generated across this point. We'll just call it the hot point, and this point, the cold point. So crucially, the ground is not connected to this at all. So whatever voltage that we are interested in is the difference between this hot and cold points. Let's just call it hot minus cold. So this thing is our audio signal. Anything that is not this is not our audio signal. So the reason that we are interested in the whole thing of differential mode impedance is that, look at this. What is driving this amplifier? It's this coil of wire, right? So what matters is what this coil of wire experiences at, well, this end, which is connected to the amp over here. So this is just the length of wire going through space, doesn't really matter. And so what we are interested in is essentially how much load is this amplifier placing on this signal source, which translated into the terms of resistance, or more accurately impedance, is going to be the impedance between the hot and the cold. So we call this impedance over here, it's the, let's use this color, hot and cold impedance over here. So what matters is the impedance between this hot input and this cold input. So let's take a look at what's the difference between differential mode impedance and common mode impedance in this case. So I think the easiest way to think about this problem is that impedance, or resistance for that matter, depends on two things, right? We know that impedance is equal to the voltage difference over the current that flows, right? So let's break it down. When we say voltage can't exist by itself, right? It has to be with reference to something else. And for current can just flow, right? It needs to flow in one direction and have a return path. So differential mode impedance refers to dividing the quantity, let's use this color, dividing the quantity V hot minus V cold over, let's just call this ID. This is going to be your differential mode impedance. That's DM. So how is this different from common mode impedance then? So now is where it gets a bit hairy. We are going to look at the common mode of this entire scenario that we have going on over here. So first, what you have to realize is that the hot and the cold inputs of the amplifier are essentially connected to transistors, right? So somewhere in the amplifier, there's going to be this transistor. Could be a FET, could be a BJT, don't really matter. So it's going to be transistors, resistors, whatnot. So the crucial thing to realize is that eventually there is a path from this hot input over here that goes to ground. Likewise for the cold input, somewhere in here there is a path for the current to flow through some sort of impedance. Oh, that really should be an impedance here, sorry about that. Through an impedance down to ground. Now here's a question to think about. What is the potential of the coils in here relative to ground? Imagine that somehow I opened up the microphone and, well, there's all this like wiring and windings and whatnot here, right? I somehow connect a piece of wire here over to these windings, and we'll just neglect the impedance of the microphone windings here. It doesn't really matter for our discussion today. I'm just gonna connect a piece of wire over to the coils of the microphone, and I'll just drive it with some arbitrary signal source over here. And this signal source is referred to ground. Now, this is where our common mode impedance arises. So, I'm having trouble choosing colors here. Let's see, let's use dark orange. So crucially, now there is a path for current to flow like this, right? Goes up, goes into the mic, and we'll just assume that this entire thing is symmetrical just for the purposes of simplifying the discussion. It splits into two. Then it goes through the wire, goes through everything over here, blah, 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 comes here, goes into this node over here, and goes through whatever transistors, gates, and whatever, goes back to ground. And since ground is the same everywhere, well, for this discussion it is anyway, so the current can take this path over here and go back over here, right? Same thing happens on the hot branch. So current flows, just flows over here, comes here, takes this path, goes down through whatever gates, transistors, and whatnot, goes down to the ground, and flows back, joins this current from the hot side over here, joins it, and goes back into our, voltage source over here. So the common mode impedance, in this case anyways, that is seen by our voltage source over here, let's call this VCM for common mode. What's the impedance seen by this voltage source over here? Well, it's just gonna be whatever VCM is divided by, what happened? Divided by the current that is sourced by VCM, ICM, right? So this gives us the differential mode impedance. And this is going to be equal to, let's say, Z1, Z2, Z1 paralleled with Z2. Okay? So this is our ZCM. Now, in the context of our course, the whole situation with the long tail pair thing, it might be useful to think about it this way. Let's just say that this resistor isn't there anymore. So we just use the resistor as a surrogate to carry out our discussion of differential mode impedance. So now I want you to think about what the differential mode impedance across the hot and the cold is. What is a signal going to do if it's present across the hot and cold terminals? So let's follow the path then. Let's say we have a signal, a current for that matter, coming in. Let's say we have a signal or a current coming in over here. It goes through here, follow the money, goes into here, goes down through to earth, goes back up Z2, out the cold side, and back, right? So eventually it makes its way over to here and is seen by this, the coil of the microphone. So this is our differential mode impedance. Take a look at how the current travels through this. The current goes through Z1, through Z2, and back, doesn't it? So our differential mode impedance is essentially equal to Z1 plus Z2, right? So the next time you come across differential mode and common mode impedances, I want you to think about it like this. The differential mode impedance is the impedance that would be seen by a signal that is present across our hot and cold lines. The common mode impedance is the impedance that is going to be seen by a signal or a current or a voltage or whatever that is present across both the hot and cold sides at the same time. I like to end this discussion with just a little bit of a rant maybe. In the electronics community, a lot of people like to say, oh, the impedance seen by something. Well, what does it mean to see an impedance? Well, I like to think about it this way. We know that impedance is just equal to voltage over current, right? So what is crucial is, let's say you have 2 points. The impedance seen across these 2 points is going to be the voltage that is across these 2 points divided by the current that flows in between these 2 points. So in this case, let's think about what the differential impedance of this entire system is going to be in terms of being seen by something, right? So what matters is what the microphone sees as its differential impedance. So the signal that we are interested in, or in other words, the audio signal, is going to be present across the hot and cold. So what the audio signal sees is the differential mode impedance. Why is that? Because the audio signal exists across these 2 points. And what is the impedance across these 2 points? Well, it's the voltage that is present across these 2 points divided by the current that flows between these 2 points. So going back to the whole current tracing thing, the current goes here, goes through the wire, up into the hot, through Z1. So we have a cumulative, if you will, impedance of Z1, down to earth, back up through earth, goes up through Z2. So now our impedance is Z1 plus Z2 and goes back through the cold and all the way back to this node here. Or, well, to the mic, if you will. So our differential mode impedance is Z1 plus Z2 in series. As for the common mode, if we have some sort of voltage that is driving this end of the microphone, well, what is the common mode impedance that is seen by this? Right? The common mode impedance is going to be whatever voltage is present here, with reference to ground, of course, divided by the current that flows across this entire wire pair as one through these 2 resistors in parallel now, crucially, and coming all the way back through ground. So that is why the common mode impedance is Z1 parallel with Z2. It's to do with how the current flows. And I guess the key thing to take away here is that differential mode and common mode are really just terminologies that we use to name impedances that are present in this sort of a differential signaling scheme.